Welcome back to the last part of the third lecture. Now we're going to look at the Poisson distribution, which is quite similar to the binomial. In fact, it kind of stems from it. We can derive it. So what's the idea? Think of a large number problem like, what are the chances that someone in Germany wins the lottery? So we've got a large sample of people playing, something like 10 million, and we've got a tiny probability, 10 to the minus 9 or something like, or 10 to the minus 8 actually. So in combination, if you put it into the binomial distribution, we get a 30%, 35% chance that this happens. But it's a combination of something large number combined with a very small probability. So large times small equals this. And that's numerically sometimes a bit challenging. And the idea of Poisson is to kind of simplify the binomial formula to get to a more simple formula that describes exactly this problem. So we see here again this binomial, and if we go up with n number of participants or number of draws or rounds, then this number here, n factorial, absolutely goes through the roof. It becomes really, really big. And on the other hand, small probabilities, this factor here, p to the k, that's going to become super small. So that's the challenging bit. Now what we're going to do, and we could calculate this in detail, but I think it's not super necessary to go through the calculation itself. It's more like a limit calculation that you've done in mathematics and analysis. If we keep the product n times p constant, so n goes up and p goes down, but the product of those two remains constant, then under this assumption we can simplify the whole thing and we get to this formula where mu is the product of n times p. Mu is this kind of constant that we're talking about. And basically it only contains the factor mu and the number k, which is the number of successes. So we got completely rid of the number n, so total number of attempts or repetitions is not in there, and the probability is not in there. So no large and no super small numbers anymore, only this mu. Okay, let's look at this. What does it look like? So as it turns out, this mu, n times, here was n times p, that is also the expectation value. So we have a formula here that incorporates exactly the expectation that we have. So what are the chances of k successes when we have an expectation mu? And we can use the Poisson distribution with that. Just put it into the formula and the distribution looks like that. So if we have an expectation of 5 is here, then it's not unreasonable that 5 is like at the peak of this distribution. It's like the highest probability, but then we could also expect a bit less or a bit more. Seems fairly symmetric. The CDF again looks like that. There's not much to say about this one. And then we can change mu, make it smaller. So everything kind of shifts more to the left, and that's something we've already seen with the binomial distribution. That becomes more and more skewed, and yeah, different shape to the left than to the right, obviously because there's more space to the right. And to the right we see this kind of exponential decay here, yeah, that comes down. Okay. If we compare the two, just to see, because we derived Poisson from binomial, so there must be some sort of similarity. Let's start with like n equals 10, and expectation value is 5. Yeah, that would equal to like a probability of 0.5. Yeah, as mu is n times p. Then we see that like, yeah, fairly different in that case. So the Poisson is the orange one. So this is Poisson, and the binomial is the blue one. And yeah, they're not too similar, but what we can do is we increase the number n. So now we go for this n goes towards infinity, and for n equals 20 it already looks a tiny bit better. 50, getting there. 100, 1,000. So now for n equals 1,000 we definitely can't really tell a difference between binomial and Poisson. They exactly look the same. So that is like how we designed the whole thing. So if we're like 100 was already quite good. So if we're in the order of magnitude around 100 to 1,000, we can definitely use Poisson. Maybe even before. Yeah, it always depends on like how accurate you want to be. Okay, let's try it out. And what we first want to find out is, every week on average one person wins the lottery. So that's my expectation, one person. What are the chances of 2 people winning in 1 week? Interesting for the Poisson distribution is we only need very little information. Like we don't need to know how many people are taking part. We don't need to know any more details on probabilities. It's just all we need is our expectation, the average. And I've got 4 numbers here. You will, if you use Excel or MATLAB, you can just fire away and calculate it. If you're using the table below, I just want to quickly explain what is meant here. So obviously these are the lambdas to the right. With the lambdas I mean the mu's. So mu equals lambda, it's just different notation. So depending on where we are, you use a different column. Then on this axis here, you've got the x. This is then number of people winning. So this is x. The only thing that's important to keep in mind, these numbers here, they are the CDF numbers. So this is the CDF. What does that mean? For example, let's say if we have a mu of 0.5, just for example, and you look at this number here, it says 98.5%. Obviously that's not 98% chance that we've got exactly 2 people winning. It means that we have 2 or less. So basically that 2 here is the sum over the whole column down to 0. Yeah. Hence, at the bottom here, it all adds up to 1. Yeah, that's where the CDF kind of converges to its maximum value 1. Okay, so that's how the whole thing has to be read. Okay, have a go. Okay, exactly. The answer is 0.18, so 18%. Where do we find this? Okay, we need, we've got a mu of 1 over here. And this is our column. We are here. Now, we want 2 people winning. X equals 2. Now, what we get here, this is x smaller or equal than 2. So that's also including x equals 1 and x equals 0. So how do we get x only equals 2? Well, we take those 2 values. This one here is x smaller equals 1. And we take the top one, probability of the top one, no, the other way around, probability of the bottom one minus probability of the top one. Let's move it around. Minus this one. And that's exactly the 0.184. Excellent. So with a CDF, it's, yeah, if we want to equal something, it's a bit more tricky. We need to take the difference. But if we ask something, what are the chances that at least 3 people are winning, then it would be easy to just, yeah, take that out of the table. We don't need to add lots of numbers. All right, let's try another one. Oh, this is just to confirm how it's done in by the computer, and also like how the Poisson and the binomial are really similar. So we would only get a difference here in the last 3 digits. Okay. Right, so let's try a different one. So every week, on average, 1 person wins the lottery. What are the chances of 3 or more people winning in 1 week? Exactly. 3 or more. We easily get this by saying, okay, there's 1 minus 2 or less. No? And then 2 or less is this one here. 1 minus this is the 8% that we find. Brilliant. Let's do another example. Let's switch over to football. So during football is kind of an interesting example, because you could say, you know, that in a football game there's like a lot of attempts to score a goal, but the probability each time is fairly small that actually happens. So we've got this like lots of attempts, large N, small p situation, and the mu is then 2.5 goals per game during the World Cup. So what is the probability of seeing a game with 4 or more goals? Exactly. So that's 1 minus 3 or less games with that probability. So 3 or less is this one here. 1 minus that, 24%. So that's the right answer. Cool. One last one. What is the probability of seeing a game without any goals? Exactly. That is simply this one here, 8%. Yeah, at 0, the PDF and the CDF are identical. Just a word about expectation and variance. So obviously the expectation value of a Poisson distributed one is mu. Yeah, that was like from the onset our expectation, just like we know for binomial it's n times p, which is exactly mu. Interestingly, the variance is also mu. If you want to see the calculation, it's a bit longer. You can find it in the book that's referenced at the bottom. You would mostly, if you're not using the tables like in the exam or the lectures, you will probably use MATLAB with these two commands, or Excel, and that's how you can calculate everything you need. Brilliant. Then thank you very much for your attention. I hope you enjoyed this little start into the discrete distributions, and next lecture we're gonna start looking at the most important one, the continuous and the Gaussian distribution. Okay, have a good week. Bye.